Okay, I think we are good to go. So, good morning, afternoon, everyone, and welcome to today's webinar, where we will be discussing survey correction and specifically the advanced HiFi Nav correction offered by our integration partner, Superior QC. I'm Jay McClelland, Innova's Technical Manager, and I'm delighted to be joined today by Joel Dunn, who's a Senior Technical Advisor with Superior. So thanks for joining us today, Joel.
You're very welcome, Jay. Thanks for having me on.
So before we begin, please note that this webinar is being recorded and the recording will be available on both companies' websites by tomorrow. So today we'll explore high fidelity navigation, or HiFi Nav as it's more commonly known, which is an advanced survey correction method developed by Superior. We'll start with a brief introduction to both companies and their roles in the industry, followed by an in-depth discussion on the intricacies of HiFi Nav and its unique advantages. We'll conclude with a Q&A session, so please add your questions to the Q&A section at the bottom of your screen, and we will answer these at the end. For those of you new to Innova, we specialise in industry-leading software solutions for the energy sector, focusing on directional drilling, well planning, and drilling engineering. Our goal is to enhance data flow and simplify complex processes through cutting-edge software and API integrations, which enable efficient cross-platform communication. And these capabilities allow us to collaborate with partners like Superior QC to integrate advanced functionalities such as HiFi Nav directly into our platform for a seamless user experience. I'm now going to pass you over to Joel to introduce himself and Superior.
Thanks, Jay. As you mentioned, I'm Joel Dunn, Senior Technical Advisor for Superior QC. We are a survey correction and QC company. We were founded in 2015 by Chad Hannock and subsequently acquired by Patterson in 2018, around about the same time as their acquisition of MS Directional. Since then, we've grown to become one of the largest survey QC companies in North America. We're based here in Houston, but operate globally, providing various levels of survey correction and survey QC services to operators all over the world. It's a little bit about us.
Perfect. So thanks, Joel. So could you sort of tell us a little bit more about the different corrections that Superior has to offer?
Sure, yeah. For those listening who aren't familiar with survey corrections, let me just describe what we mean by the term survey corrections. In general, survey corrections are just a way to analyze and correct for errors in the measurements that are used to calculate directional survey values, which in turn are used to calculate the position of the wellbore. So as you know, any measurement you take with any device or apparatus has error associated with it. An MWD tool is no different. The directional sensor and the MWD tool downhole measures the gravity and the Earth's magnetic field along all three axes. It sends this information uphole where it's used to calculate the inclination and the azimuth of a directional survey, and along with some other qualifiers that are used to QC the survey itself. And some of the errors in these measurements are errors in the sensors themselves, like biases and sensor scale factors and like various misalignments between the sensors. While some of the other sources are associated more with the reference field, like the field strengths and declination and things of that sort. But in total, there are 27 sources of error that will potentially affect this calculation of the inclination and azimuth, with the biggest impact being primarily on the azimuth. And given that these errors are always present, at least to some degree, you can use a survey correction algorithm like multi-station analysis, which is probably the most common, most familiar to everyone listening. You can use these methods to estimate the errors and actually correct for them. So the result of this is a corrected inclination and azimuth that is, in theory, more accurate than the values that you would have calculated just with the raw measured values, right? So early on as a company, we at Superior provided multi-station analysis correction, just like those currently available throughout the industry, until we deployed our fault detection, isolation, and recovery algorithm, our FITR as we call it, which is just the acronym FDIR. And FITR was developed specifically to address some of the limitations and inconsistencies of just traditional multi-station analysis and just generate a more accurate, more robust correction. Like multi-station analysis, FITR is still primarily an azimuth correction, but it's not really constrained by a lot of the limitations of traditional multi-station. So for one example, the most prominent limitation of MSA is that it's only able to effectively solve for up to 6 error sources simultaneously. This means that someone has to choose which 6 of the possible 27 to correct for. So ultimately, that means that there's no unique correct solution, but instead just like literally thousands of potential solutions and combinations, all with some degree of correctness. Where Fitter, on the other hand, can statistically evaluate all 27 sources, and it provides a single correct solution for any given data set. A good way to look at all of this is just kind of in terms of generations of survey correction technology, starting with field acceptance criteria, where you just kind of get the survey up and you compare your measured values for gravity, magnetic field strength, and dip angle to what the reference is supposed to be. It's not really a correction, but you could kind of consider that the first generation, followed by single station correction, which allows you to correct for drill string magnetic interference. And that's followed kind of by probably a pretty big leap with MSA, which allows you to correct for multiple sources. And if you consider that third generation, and looking at it this way, we really consider Fitter to be a fourth generation solution, because despite some overlap with MSA, it's really a technological leap and kind of really in a class of its own. So it tells you we've done a lot to ensure we're providing a most accurate wellbore position, at least in terms of the azimuth, which translates to lateral left and right placement, northing and easting position. Think well spacing, for instance. But there's still room for improvement, and we recognize that in the overall accuracy, especially when you consider the often overlooked or even sometimes flat out ignored TBD error in the TBD plane, right? And that's kind of where you have to look to a fifth generation technology like HiFi Nav.
Cool. So yeah, I mean it's actually really interesting to hear about the evolution of the sort of survey correction side of things. So with that in mind, could you explain a little bit more about HiFi Nav?
Sure. I'll start off probably by kind of laying out the problem that we're trying to solve with HiFi Nav, which is TBD error. The TBD error we're looking at is primarily a limitation of minimum curvature, which is kind of the industry standard method used to calculate the wellbore position based on survey data. So just about every directional software out there, in fact, all the systems that I'm aware of, use minimum curvature as the default to calculate the wellbore position. And this method basically just involves connecting 2 survey stations with a smooth arc, minimum curvature. So the problem arises when the path between those 2 surveys doesn't really resemble a smooth arc. And with directional drilling, it usually doesn't. And as the distance between those survey intervals increases, the potential for this error also increases, because you're losing information about the true wellbore shape due to the smoothing effect of the minimum curvature. All right, so I'm going to just share a little graphic here, kind of give a little better visual on this. So consider a 2D example. So we're going to talk now about how this contributes to the TBD error. It's basically due to a phenomenon known as Stockhausen effect. And that's really the primary contributor to the type of error we're solving for here. So if you consider an example here where you have a survey at 70 degrees inclination, followed by another survey 1 stand later at 90 degrees, minimum curvature will calculate the displacement or the change in TBD using a smooth arc as shown by the yellow line here. However, if the angle was built during the first part of this course length and then rotated out, as shown by the red and white segments, respectively, for sliding and rotating, the actual vertical displacement would be less than the minimum curvature calculation, meaning a shallower position. On the other hand, if the first part of the course length is rotated and the angle was built toward the end, the vertical displacement would be greater than the minimum curvature calculation, resulting in the actual well placement being a little bit deeper, right? So how do we resolve this difference? The solution is to actually capture the true shape of the wellbore. And so one way that you could do this is by taking more surveys. But why would you stop and cycle for additional surveys when you have reliable information about the actual well path over that entire course length? I mean, couldn't we use that information to calculate what the inclination and azimuth should be based on this data? Well, actually, yeah, we can. And that's exactly what we do. So if we insert trajectory waypoints between the two static surveys that capture a more accurate representation of that wellbore trajectory, that well path, we could still use minimum curvature to calculate that wellbore position, but we minimize that error since the intervals are a lot shorter. So just to kind of break it down really quick, to break down the process and look at like what we're doing in step by step is we start with a survey with 6-axis data. Some basic information about the steering tool type that we're using to steer the well and the capability in terms of yield. And then as we drill ahead, we pull some data from EDR to determine when the BHA is and is not actively steering. And we use this information to model the trajectory and insert trajectory points, which consist of a measure depth, an inclination, and azimuth as we drill ahead. And at the next survey station, a survey is acquired. And in the event that there's a slight difference between the inclination of the survey and the projected or modeled value at that point, the steering yield or the rotary tendencies or even both are refined, and the trajectory points for the latest interval, they're updated, and then we use those new values to project forward until the next survey, and then the process repeats itself.
Okay, so you've mentioned so I've probably got a couple of questions that tie together here. You've mentioned that you need additional data, and you mentioned that you get it from the EDR. So I guess first question would be, what additional data do you actually need? And is there any other sources other than the EDR that you require? Like, for example, does the DD or the MWD engineer have to provide additional data over and above the EDR data?
So really, I mean, the only data that we need in addition to the six-axis survey data that we would need for the fitter or multi-station piece of it can be obtained from the WITS-ML stream from the EDR. Most of what we need is like surface sensor data. However, we do need the MWD to WITS over the tool face to the EDR in case of a conventional motor BHA. I believe that's pretty standard practice on most rigs nowadays. So that's really all we need from that standpoint. We can also do this, have this capability with rotary steerable, and if RSS is used, we will also need them to WITS over the RSS tool face and the steer ratio or steer force. We need that WITS over to the EDR as well if that's available in real time. But other than some routine initial setup at the beginning, the rest of the process is automated.
And kind of playing devil's advocate, if there was a situation where you were on a rig that didn't have EDR or something went down with the EDR system, are you able to use, for example, the DD slide sheet instead? Would that give you the information that you need to be able to do the correction?
Yeah, I mean, we prefer to get the data automatically from the EDR, but it tends to be more accurate. However, in the case where that data is not available for whatever reason, we can also, we can use slide sheets from the directional driller, at least for motor BHAs, because really at the end of the day, we just need to know where, when, and in what direction, and the magnitude of the well where it was being steered. So that's kind of what we need to know at the end of the day. And coincidentally, actually doing this automatically isn't an easy task. While it's pretty simple for a human to identify sliding or rotating just by looking at an EDR trace, programming a computer to be able to do that effectively and accurately, especially when you're out in the lateral drilling and rocking the pipe and there's torque involved, it's not quite as simple as it sounds. So in order to do that, we actually built and trained a neural network, which has been working out pretty well for us to identify those slides. And so taking that, kind of going back to the whole process, and since we're able to determine like when the well was being steered, how far, and in what direction from this data, we can kind of grade the slide to calculate its efficiency, which is really crucial when you're trying to calculate the trajectory. For instance, if it's a poor quality slide, you shouldn't expect to get the full yield for that interval, and that has to be taken into account and things like that, right? So putting it all together, in addition to these steering intervals and the information that we're getting there, we also track the rotary tendencies, or in other words, what the BHA is doing between steering intervals or when it's not active in active steering mode. And there's a lot that goes on behind the scenes at that as well. I mean, there's some filtering that has to happen just to make sure that you're able to distinguish between more long-term formation tendencies and then like more acute changes and the trajectory resulting from like deflection off of an inclusion or stringer or something like that, which can cause several degrees of angle change over a very short interval. I mean, you want to capture those as well, but you don't want them to affect the long-term tendencies that you're using to project. So, and that's just a couple of things that you have to consider when you're looking at that. So, Putting those together, since we know where the well was actively being steered, we know what it's doing when it's rotating, we can combine this to model the trajectory between the two static points, and we're using known verifiable data to come up with those trajectory points. So at the end of the day, it's really a data-driven process with periodic and in many cases continuous validation and refinement of that model. Because in addition to validating and refining at each survey, like I mentioned earlier, HiFi Nav can also ingest continuous DNI data to verify and validate the model continuously between survey points as well. So it's kind of how it all comes together in a nutshell.
Okay, and how many points would you typically use or generate between static surveys? I mean, is it like a fixed number, or does it vary depending on the data that you're working with?
So we typically insert 6 actual trajectory points between 2 static surveys, taking a typical stand length to be 90, 95 feet. So that results in about 13 to 15 foot interval spacing. So we assume the typical stand of 95 feet. So if you miss a survey and you've got 180 feet between the two, then we would insert 12 trajectory points in that space, right? So that's kind of how the logic works. And we use this because we found at this interval you can really adequately capture that trajectory and that shape that you're trying to capture, and you can retain the accuracy of minimum curvature as well, without really making any assumptions that exceed your resolution capabilities. So, and really, if you go any shorter than this, you start to get diminishing returns, as you're not necessarily capturing the trajectory more accurately for what we're trying to do. You're just really adding additional lines to the survey log. And then again, on the other side, if you start to increase that interval further, you start to lose some of that resolution and begin smoothing out those steering events, which again results in the accumulation of this TBD error.
So yeah, it's actually really interesting. So there's been a lot of work done on finding the sort of optimal spacing for these additional points that you're going to use, opposed to just saying, well, we'll put in as many as we can because that will help the accuracy. Actually, not necessarily the case. 6 foot. So if we think about that in terms of a 25,000 foot well, which will have 200 to 250 survey points on its own, with the HiFi Nav, you're then looking at having 6 times more data points that the field engineers have got to deal with. Have you put anything in place that will help them deal with that volume of data?
Yeah, actually, we have, and then you're correct. Yeah, in addition to your static surveys, you're going to get these trajectory points, which they're treated as surveys in the survey report. There's no 6-axis data associated with them, but they do consist of a measured depth, an inclination, and azimuth, and they need to be included in that survey report to capture the actual shape of the wellbore, which is what compensates for that Stockhausen effect. So essentially, yeah, you're handling 6 times as many surveys in the standard report. Again, for perspective, on a 20,000 foot well, you're looking at typically 200 surveys, but with HiFi Nav, you're looking at a survey report of like 1,200 entries. And to be honest, yeah, handling all that data can be cumbersome operationally, which is why we put a lot of work, a lot of resources into making it easier to transfer all this data, mainly through using integrated APIs to replace the need for all these manual processes like copy and pasting, which has the potential for mistakes and human error and a whole slew of other things that can cause problems. So initially, when we started doing the API work, we were focusing primarily on transferring that data back and forth between the Irish system and the MWD system, since on the rig site, they're typically the primary person that manages these surveys. But we've also done some integrations with geosteering softwares, data analysis platforms, and things like that. So really,
Yeah,
at the end of the day, the end goal is just to have up-to-date and consistent survey data across all the systems that are using our service.
yeah, and it makes sense that you've got that connection with MWD because they are effectively feeding you the information, you feed it back to them. In terms of sort of field operations, the general sort of workflow would be that the MWD would then pass that across to the directional driller, who would then either manually insert it or copy and paste, as you mentioned. So there is the additional steps there involved with the MWD getting it to the DD. Has there been anything, from that side of things done?
Yeah, actually, so I mentioned we're focusing primarily on the MWD side, but one thing that we realized pretty quickly as the HiFi Nav started to gain traction was that while we had done a lot there, we were still lacking a really efficient way to get that data transferred between the MWD and the directional driller, who is a crucial part of this whole process. In most cases, yeah, they were still relying on, copy and paste and these manual processes to transfer that data, open it up for mistakes and all kind of things like that. So, and it also resulted in additional work for the directional driller, which is never a good thing. So that's why the integration with Well Seeker has been so impactful. It gives the directional driller the ability to, with a click of a button or even automatically, to update his survey listing, like directly from our definitive survey list, which is the same place that the MWD is pulling his list, as well as geology and everyone else that's connected to our system. So
yeah, so that's a perfect time for me to just share my screen very quickly, just to show you. I mean, as we talked about, the idea behind the integration is to effectively simplify and streamline the handling of new surveys, and cut down on the sort of manual data entry, because inevitably you put these things in, you've got other things to do. It can be a stressful environment if you're if things are very, very busy, you're drilling quickly. So even the most diligent person can make a mistake when they're putting surveys in. So we've made this as simple as we can. It's as simple as opening up the survey correction provider's settings, selecting the provider, in our case, Superior QC HiFi Nav, username and password, which would come from Superior. We select our update to auto, and it can be pulled manually at any time, and your update rate. You hit save, and you can close this. And basically, anytime a new survey is put in, or a corrected survey is put in at the Superior side, when we check for the update, it will then pull it down directly. The DD doesn't have to click on a button, doesn't have to do anything. It will just pull directly into the survey listing for them. And if there has been a few surveys that have caused a larger correction on previously corrected surveys, they will pull in as well. So instead of having to delete and pull them back in, it will keep you up to date. So you're always up to date with the with what is basically on the corrected Superior side. So this in itself reduces the time it takes for the directional driller to actually get the surveys, and it all but eliminates data entry on the at the field side. So really, whether you're getting one survey or 100 surveys or 1,000 surveys, it all just comes in very quickly and easily. So I will stop sharing my screen, because that is as simple as that integration side of it is. But what that does is it leads me up to my sort of final question before the Q&A, and that would be, the purpose of survey correction in general is to improve on our positional accuracy and reduce our uncertainty. So for the HiFi Nav, how do you actually sort of quantify this? By that, I mean, like, for example, do you have an IPM that can model this?
so backing up just a little bit, so the positional accuracy is improved by obviously compensating for the Stockhausen effect and correcting for that TVD error that otherwise would have accumulated if the true wellbore shape wasn't captured by these trajectory points, right? So if we look at that in a little more detail, let me bring up this. So yeah, to kind of give you a visual, here's a 3 sigma EOU plot at TD for a well that had a lateral correction that we were able to correct with the MSA, or the fitter part of this, of 126 feet. Again, this was due to the azimuthal correction. And this particular well also had about 37 feet of TVD error due to a combination of sag error, as well as the Stockhausen effect that we kind of covered in detail earlier. In this example, I believe 11 feet of this total 37 was sag related. The other 26 feet was a result of the Stockhausen effect. And then that ratio can typically change when we see a combination of both. But you can see the relative difference in the position of the raw final position, which is the blue circle there, and then the corrected position, which is the orange triangle there centered at the origin. And yeah, since these surveys are corrected in real time, you'll see this on the plot, but the surveys that you're getting are also corrected in real time. So the wellbore position that you're calculating based on those surveys is the most accurate, and all these corrections have already been taken into account. So, and if you also notice on these plots, you'll see that there's 3 different ellipses of uncertainty, or EOUs. These ellipses quantify the positional uncertainty associated with each type of survey. So, for instance, the blue ellipse represents like the cumulative uncertainty for the raw surveys. And this is based on the ISDWSA MWD plus IFR error model, since all these were run with in-field referencing with no corrections applied. The red ellipse that you see there is the target error model, which for HiFi Nav, we still use the fitter error model. So that's what was used in the planning for like anti-collision and well spacing and stuff like that. That's our fitter ISCWSA error model. And the orange ellipse is the actual uncertainty that we were able to achieve. And that's actually calculated based on the actual data set for the well itself. So if you kind of compare these, you can see that we were able to reduce the lateral uncertainty by 46%, the left and right, and the vertical uncertainty by about 64% when we compare that to the raw and corrected surveys. And then if you want to go further and see how much better we did than the target error model, those values are about 37% laterally and 40% from that target EOU. So going back to the last question you had about the IPM, to quantify the error for HiFi Nav, we do have an IPM for HiFi Nav. It does have some lower values for some of the borehole misalignment terms, but it doesn't necessarily really reflect the amount of uncertainty reduction that's possible from addressing the minimum curvature calculation error. It's because really the structure of the current models doesn't really include terms to account for a higher survey density, aside from the newest revision 5, where they introduced the extended course length term, but that really doesn't do much to reduce uncertainty for intervals less than about 100 feet, right? So that kind of vanishes there. It doesn't really give you any upside there. So for this reason, we still use the fitter error model when we run the HiFi Nav service. But it's definitely something we're interested in looking into, and we may propose that at one of the future ISCWSA meetings. But yeah, as of now, we're still using the fitter IPM in most cases. But so if I was to sum it all up, I guess HiFi Nav really provides just about the best, most accurate wellbore position that you can achieve with MWD surveys. Not only do you get the comprehensive azimuthal correction, but when combined with a simple sag correction, you're also now correcting for actually multiple types of TBD error. So all in all, this provides a lot of benefits to everyone involved in the well, whether that's removing unknowns from the geologist and the geosteering team's interpretations and correlations, or things like revealing dog legs and tortuosity that would otherwise be hidden from the drilling and completions guys with 95-foot surveys, ensuring proper well spacing, which is important to the asset and production teams, or even something like eliminating gyro runs and uphole sections as well. These are just some of the few examples of ways that we've actually brought real value to some of our customers. So there's a lot of potential here. So really appreciate you having me on and let me explain this technology.
No, I mean that's been great. It's been really informative, Joel. Thank you. Thank you for that. We are now at the last part where we've got our question and answer session. We are hit about the half-past mark or the 30-minute mark. So we've got a few questions. We'll go through them. We'll try and answer them all. If we can't, because we've run out of time, then what we can do is we can make sure that we get answers to these questions out by tomorrow to everybody. But let me have a little look and see what we've got. Sorry, I'm just right. So first one. This is by an anonymous attendee. When geosteering, we're typically doing so based on markers. So how will having a better interpretation of the TVD help?
So yeah, this is a question that we've got before when we present this to some of the geology teams. So on a particular well, like if you're just looking at it on a one well basis, there could be an argument for that. However, if what you're trying to do is get the most accurate actual TVD, that's going to tell you where those markers are in relation to all the wells that you've already drilled on that pad. It's going to tell you where that is in relation to the future wells you have to drill on that pad, or even an adjacent pad. So kind of looking at it from a multi-well standpoint, it does add a lot of value in kind of knowing where you're really at, not just relying on those subjective markers that you're seeing. And it's actually a pretty recent case study we've done where we actually saw where we had TBD error accumulating in one direction, and then kind of things changed and it started to accumulate in the other direction. And it was actually mistaken as a fault. Because there was over a short distance, a couple hundred feet, there was a 6 to 8 foot difference in where that TBD actually was based on the error. So even looking at it from a one well standpoint, there's still a lot of value in knowing where you are TBD wise.
Yeah,
objectively. So
that makes a lot of sense. Right, next question. Do you need continuous inclination data? This is an anonymous again.
Okay. No, we don't need it. And that's kind of one of the reasons we took this approach to capture the well path with the steering, because that's continuous inclination is typically widely available, but it's not always available. So we wanted a solution that we could employ even in the absence of that data. Now, if it's available, we bring it in. It helps us continuously validate, continuously refine our model, but it's not necessary to run the service.
Okay. Next question. Is this a replacement of SAG? That's by Rashid Khan.
No, it's not a replacement SAG. It actually works in conjunction with SAG to, again, identify a different type of TVD error, right? So your SAG is basically compensating for the misalignment with the borehole of your DNI package due to BHA SAG. And that's actually going to be a direct correction to your inclination. That's going to be a value that's either added or subtracted from your calculated inclination based on where that sensor is sitting. So that's one way to compensate for the TVD error. Was one type of TVD error, I should say. The other is kind of like what we talked about with just kind of the type that's kind of really hidden there when you're calculating minimum curvature. That's kind of where the HiFi Nav really comes in, and it's detecting that type of error.
So they're used side by side.
Yeah, they're used in conjunction. You
Yeah.
can use them both, combine them. Yeah.
Okay, thank you. Next one is another one by an anonymous attendee. So that would be, what are some of the largest TVD errors you've seen? What typically causes large TVD errors?
So speaking specifically from the HiFi Nav perspective and the Stockhausen generated errors, we've seen a few upwards of 75, 80 feet on like a 10, 12,000 foot lateral accumulated by the end of it. That's probably about the highest we've seen, but we see quite a few with 30 to 40, 50 feet even, and then probably way more than you would expect around the 20 to 25 foot mark. And typically what causes these big errors from the Stockhausen perspective is when you get into a pattern of sliding. That's what we call it, pattern sliding. Whereas if you're fighting like a really strong build tendency and you're drilling with a conventional motor, so you're building, and then the directional driller is typically going to place his slide where he sees the very end of that slide at the survey point. So what's happening is you're accumulating all of this trajectory or all this well path above what your survey sheet is showing. And then that has a shallowing effect on your wellbore. Or actually it has a deepening effect because your wellbore is actually significantly shallower because you have all this building and then you're dropping it down sharply with a slide, and then you're taking your surveys at those points. So that's typically the big errors that we've seen. That's typically the reason that we accumulate such big errors on the big ones we see.
Okay, that makes sense. So we've got one here from Saeed Reman. How often is the survey data corrected? Is it hourly or daily, or how often is it corrected?
That's every survey. Every time we get a new survey, the whole process runs. The model's validated, it's refined, and so the surveys are corrected every survey. Every time you get new survey data, and then the trajectory points are inserted at 15-foot intervals as you drill ahead. It's kind of we have the trajectory points between the surveys, but we also insert those between the last survey and the bit. So we're also doing a projection based on those yield values and the rotary tendency values that we're calculating. So it's a real-time process.
Okay, perfect. Let's have a look. We've got some other questions in here. So I think we've got another one relating to SAG. Just following up my previous question, is SAG required for this? SAG is what gives the EOU reduction TVD correction. So I think that's asking.
Yeah, so so SAG is not necessarily required. I don't think there's ever been an instance where we've run it actually operationally without SAG. But yeah, you're right. In the error models themselves, since there's no term that directly takes into account the survey density and the reduction in both lateral and vertical from the survey density. Then yeah. So the biggest vertical reduction that you see is done from the sag. So if we were to run this without sag, obviously the error model would look a little bit different. It'd be a little bit I guess taller, if you will, in the vertical direction. So that's kind of how that works.
Okay. Let's find another one in here. So, are these error models the same as MWD plus IFR plus MSA plus SAG?
Yes, yeah. So I mean, we have our own for our fitter algorithm. It's been approved and it's published within the ISCWSA catalog of error models, but it's very, very similar to the MSA error model. All the values and weighting functions are very close to the same.
Okay. Right. One from Rashid Khan. This correction will implement with addition of other corrections as well, or not like MSA or IFR. I'm wondering if that means would you use, so your MSA is effectively tied up within this correction. It is part of the correction. So
Yes,
it's
yeah,
not
that
like
is,
it's
yeah.
not like you're running MSA on this side and
No, yeah, it's all
fitter.
part. It basically, yeah, the HiFi Nav piece kind of lays on top of the fitter correction or the MSA type correction. That's correct. Or basically, you can't run HiFi Nav without the azimuthal correction, without the azimuthal piece of it as well.
Okay. So another anonymous, when you say insert, is it made up point based on the data? Is it an actual survey point that can be submitted to government agencies? And how does this reduce EOU?
So, so for that question, you can say made up, but I mean it's actually derived, yes, from actual verifiable data, and it is inserted between the points. And again, it consists of a measure depth, an inclination, and azimuth. And while it's not an actual static survey point, there's no 6-axis data associated with it. It is accepted for submittal through all the regulatory agencies. So we haven't had any problems with any MWD providers or survey providers submitting those to any of the regulatory agencies. Most cases, there's just these surveys. They're just on the cover sheet. These surveys were corrected by a third party, and they list our details. And that's kind of how that process works. So yeah, they are accepted. The trajectory points are accepted in the survey listing for regulatory filing as well.
Perfect. So we've got one difference between SAG and HiFi. I think that's already been answered in terms of one of the previous questions. So I'll put that. Sorry, I'm just looking through these. If you see any as well that Joel that jump out, what about what about RSS TVD? What about RSS TVD error effect? Is it less than motor BHA?
In most cases, yeah. I mean, I did a study I presented at IADC last year in Galveston that looked specifically at HiFi Nav for rotary steerable, and taking both data sets and kind of comparing and contrasting them. Yeah, you do see quite a bit more of the accumulated TVD error in motor BHAs, and that's primarily due to a couple reasons. One of them is because typically your motor is going to yield more than your RSS. So the more yield and the more abrupt you're making these changes that you're losing in this minimum curvature over a large interval, that's going to have more of an effect and accumulate more error. The second is again, the pattern sliding. That's probably one of the bigger reasons we see the difference, because again, with the motor BHA, you kind of get into that groove of pattern sliding where it's building, you're sliding it down right at the survey point. So you're accumulating your accumulated error is more biased in one direction, if you will. Whereas with a rotary steerable, it's kind of, especially if you're drilling in like a closed loop configuration, like a whole inclination and azimuth, the tool's down there and it's kind of doing its thing based on what it's seeing from its internal surveys, and it's continuous. So that's just kind of, I mean, I guess you could get in a situation where it was building a specific amount and then it was sliding down, and that just happened to coincide with a survey point. But typically that piece of it tends to be more randomized with RSS. So while you're accumulating some above and some below, overall, your total accumulated TVD errors is typically much less, or at least somewhat less than you would see in a motor. due to
Okay.
the randomization of where those survey points lie in relation to the steering events.
Perfect. Thank you. So we probably have time for a couple more questions. So here's one here from Knut Ness. Have you compared your corrections with surveys taken with continuous MWD?
Yes, actually, that's one of the first things we started doing. Obviously, when you're developing a model, you want to look for every possible way that you can to validate it. So yeah, we've done a lot of that. In fact, in just about every situation where we modeled it and we have continuous, that's kind of one of the things we look at is we overlay the two, what our HiFi Nav model predicted in terms of inclination versus measure depth and azimuth versus measure depth, and then we lay that over with the continuous inclination and the only time it really doesn't line up is when we can go back and look if it's real-time inclination and continuous inclination data where there was an issue with telemetry. Almost always it's like an automatic, I mean, just a perfect overlay. So we do that very, very often. So
constant validation. Perfect. Right. I've got one here. So this is from an anonymous. Will corrections from a survey taken with BHA3, for example, in the lateral, adjust survey stations from previous BHAs that have already been corrected?
So that depends. Technically, yes. So the way that our algorithm fitter works is it basically looks at all the data available for that well. That's one of the other limitations that we kind of overcome versus traditional multi-station where you're kind of constricted to looking at just one MWD run. Whereas we look at all the data for all the runs for the entire well, which kind of helps us get a statistical idea of what's the best solution and what's the best set of error sources to solve for that particular well. So we do it two different ways. Some of our customers like the fully back corrected, meaning the more data we have, obviously the better our solution is, and they want to see that solution every time. They're not too concerned with some of the operational issues with quote unquote changing the correction, but we are changing it. We're making it better. We're refining it based on the more data you have, the better your solution is. But we also have an option where in order to kind of avoid some of those operational issues, we do what's real time only, where we'll correct the solution you get is a correction based on all the data that we have for all the previous runs. However, that's not going to affect once you get that correction stays the same, and then we just kind of append it versus changing everything back. So we can do it both ways, and it just depends on the amount of the accuracy that you're looking for that you really need.
Okay, right. I think last question. We do have more questions here. We're kind of run about 15 minutes over, so we'll answer one more question, and then what we'll do is I'll make sure that the questions do get answered. So we will put some answers to those questions on when we post the recording of this tomorrow. So the last one that we can answer just now is you mentioned eliminating gyros. Can you talk a little bit more about how HiFi Nav would allow that?
So we've done that for actually a couple large operators in the Permian Basin, where they would typically, part of their program was to either at kickoff point or even sometimes at the bottom of the curve to drop a gyro to get kind of a better, more accurate interpretation of the TBD at that point, because again, 90-foot surveys don't capture that Stockhausen effect, and a lot of them have seen in the past that the calculated TVD based on the minimum curvature 90-foot surveys was different than what geology was telling them it should be. So their solution historically to that was to run a gyro, but with the HiFi Nav solution, you're kind of getting that increased density and that compensation for that TVD error in real time, so it can eliminate the need to run that gyro at all and still have an accurate position of where you are TVD wise.
Perfect. Well, I think unfortunately we've run out of time. There's been some really good questions, and there's a few other questions we just, as I said, we haven't had a chance to get to. So apologies for that. We will get some answers for those questions. The recording for this will be available on, as I mentioned earlier, on both of our websites probably by tomorrow. So for anybody that wants to go back and look at it and I'd just like to finish by thanking Joel for joining us today. It's been really interesting to learn a bit more about HiFi navigation correction. And thank you to everyone who has joined us and asked questions, and we look forward to having you at our next webinar. Thank you.